total literacy that's set down by Meyer, and we are getting.
All right, just before we go to the library, let me give you at most a 10-minute review. It's gotta be able to say things well. I mean, what's been our biggest struggle all year? Writing it out, saying it. Yeah, and it's not just you, it's always true. So we'll continue to work at that. So how about some review questions? This is the histogram of what? Of the height of the population. This, however, is called a sampling distribution. Yeah, it's every single sample. It's the histogram of every single sample you've ever taken, of size 2. And this happens to be a sampling distribution, so it's every single sample you can take of size 3. We noticed some things. What's true about all 3 of them? Same what? Yeah, the same mean, okay? We'll continue to say this. Hey, sometimes your sample mean is way too low, and sometimes it's way too high. But on average, it's just right. That's the Goldilocks thing. It's always going to be that way. Okay? Say that a different way. Okay, the expected value of X bar is mu. So mu is the mean of the population, and X bar is all these other sample means that we get. Okay, say that a different way. Okay, X bar is unbiased. What does that mean? Sometimes it's too low. Sometimes it's too high, but on average, that's exactly what that means. Don't expect it to be right every time. That'd be silly. We're never going to get this right. We won't get it right every single time. But on average, it does exactly what it's supposed to do. We just said the same thing 3 different ways. Sometimes it's too high, sometimes it's too low. On average, it's just right. On average, it's just right. These things say exactly the same thing to me. And at some point, it'd be good if they said exactly the same thing to you as well. That'd be nice. We also noticed that as you go, this I suppose you could call this a sampling distribution, but the samples would be of size 1. Okay, as we move from here to here to here, what's true? The variance decreases. Okay, if for no other reason than this, when you start taking samples of size 2 and 3, you can't get that as your only data point. So look at it this way: as you make your sample size bigger, you throw out the samples on the very ends. Those can't even happen anymore. So we know that the variance has to shrink. In general, and we already took a sample of size 3, that's half the population. They generally don't do that. They generally don't have time for that or money for that, but that's the idea. So a couple of things we already know. The mean of the sampling distribution and the mean of the population, same thing. And as you take a bigger sample size, the variance of the sampling distribution shrinks and shrinks and shrinks. Okay? I didn't keep up the results from yesterday's. I shrunk it down so we could look at it a little bit easier. So for the people that haven't seen this yet, we asked a question, if you had a chance to take this class over again, would you do so? And 60% of the people said yes. And then we just took a bunch of samples. So rather than talking to all 25 people, we just took a bunch of samples. Nobody got a sample with 0 people saying they'd take the class again. But a few people got samples with 20%. Isn't that pretty far away from the real answer? Yeah. Hey, that didn't happen very often, did it? Aren't these 2 the closest you're going to get to the real answer of 68%? And guess what? They happen most often, didn't they? This is not the sampling distribution. We did not have time when we did the calculations yesterday. If you were going to take samples of size 5 from 25 people, that's over 53,000 samples. We didn't have time for that. This is not the sampling distribution. However, it is lots of samples, isn't it? Okay. I wonder what the average is. Pretty close to. Yeah, it's pretty close to that. Nick did the math real quickly because he just counted things. I think you got about 70%, did you? Pretty close. So the mean of this is 70%. It's still pretty close, even though it's not the sampling distribution. The mean of that is still pretty close. What would happen if I, instead of taking samples from this, how you write sample size, what if I took samples of size 10 instead? Once again, do you understand? Because there was only 7 people. There were 7 people that said no, which is fine. If I took samples of size 10, do you understand this couldn't even happen anymore? It would be impossible. Oh, this 100. I'm sorry. This could happen, couldn't it? because these are people saying yes. Okay, but it would still shrink some of these on the ends. In general, as the sample size goes up, the variability goes down, down, down. The one difference here is I can't even draw a picture of the population, because how do you draw a picture of yeses and nos? Hey Taylor, you made it, huh? Sounds like you had fun coming up. Alright, that's the one difference. I can't even show you a picture of the population here. It's just a stack of yeses and a stack of nos, but the same kind of thing happened. Here we would write this differently. Did you know that sometimes the sample mean is too low? Did you know sometimes the sample mean is too high? Guess what's true on average? Can we say that a different way? The expected value of p hat, we're talking about proportions now, aren't we? So be careful, we're going to flip back and forth. These are not x bars, are they? They're not the mean of anything. They're the proportion of people who said something. That's p. This is the proportion of the population, which we actually know this time. These are the sample proportions, and just like I wrote the expected value of x bar is mu, this is how you say this kind of proportions. And for good or for bad, we're only going to measure two things for the rest of the year. Sample means and sample proportions for 3 months. So that's why I'm spending so much time on it. This is the basis of the next 3 months. If you get this, you should be all right. If you don't, you're going to be struggling forever to not get the terminology down. So don't let that throw you. Do your things. We have standard deviation down here, and there's a formula for that we've used before. So we're going to flip back and forth between sample means and sample proportions. That's the only two things that statisticians ever measure anyway. I'm going to take a minute and turn this off. In your packet, would you try to find